Hello, this is Verde Arbusto, and this is the Schumann Resonance Harmonics channel on Facebook and YouTube, or I guess YouTube and Facebook. Thank you all for being here. I appreciate the love and support. Remember, like, share, comment, and subscribe. And I appreciate everyone for being here, the comments and everything. It's 26th of April. It's like 2:40 in the morning, and I'm trying to be quiet because there's people that are assumedly sleeping upstairs, although I think I hear someone walking around. I've already kind of done the video, the introduction to this. Usually I'll take like 10 minutes and do some introduction, but this one wound up being a little bit longer, and I basically talked about Chernobyl. It's the anniversary of Chernobyl. And I don't know. I think I might post it on my website and then have a link to YouTube. I don't know. I got options. All right. So this video is about we're looking at this right here. This guy right here. So, people are calling it's been this thing. I got posts on the Facebook group, or one of them, that it looked like a Punisher. If you've seen that, the big Punisher, the movie. I'm not going to put up the image of that. Hopefully you know what it looks like, but it's like basically a skull and elongated teeth or some shit. And people are saying it looks like a round object in there. It's it's a planet. They always say, it's showing a planet, as if this is an optical telescope. I don't know what people have in their heads about what the Schumann resonance spectrogram is showing, but you'll get these kind of propositions from people that it's a planet or it's a sphere. And what this makes me think of is the cave drawings, right? The anthropomorphize. What that is it's pattern recognition. People need to recognize patterns in random information. Signal to noise ratio. I talk about this. The signal is information that you want to keep. The noise is stuff that's in the background. So we filter the signal to the noise. Patterns are a form of signal, right? So in amongst all the noise that's here, people don't know what they're reading. They really don't. I mean, I've given a bunch of videos. I've explained this to people. I don't know, maybe 100 people have benefited from my videos. Like, if that, 50 people maybe, I don't know. I can give you 20 people that I can think of, 25 people that I know of, who have benefited from my videos. The rest of the world all follows the more simpler version, which you can find thousands of people following these people on YouTube. Okay, so those folks are the ones that give you a more recognizable, domesticated pattern to go by in amongst all this pop modern art. Right? I kind of compare it with that way of looking at the Schumann. That's, I think, I get the impression that some people look at the Schumann resonance spectro as either modern art, or they look at it as a societal mood ring, in amongst other things. Okay, but it's always some interpretation in there that's not supported by the actual data. Okay, and so that's sort of what this is talking about. That you see, we have our regular spikes of amplitude. All right, now you'll notice here that these are all roughly similar in shape. Okay, I call these like nested dolls. Right, that's the expression I use, nested dolls. You can see how the shape fits nicely one in another. And if you know the modes, as I've talked about, the modes are mathematical representation of a size and a shape of a wave. So the modes are a way to break the wave, the spectrum, the full range of signals. How to break that full range of signals into like bite-sized pieces based on the mathematical formula of, again, the size and the shape of the wave. So it's like if you cut a pie into pieces. If you had bigger pieces, you'd cut a piece of, a pie into 4 pieces, you'd have a wide shape like that, right? If you cut it into more, you'd have a shape like that, right? So that's what that's doing, is it's giving you like sections of the pie. If you saw a 90-degree angle or 90-degree angle, you would know it's a quarter of the pie. Or if you saw a 60-degree angle, you would know that it's maybe 12 pieces of the pie or whatever. I think that 60 is the 12, I forget, 360, yeah, all right. So based on the size and the shape of the wave, mathematically, if you know, you can tell what part of it, how big and all of this, based on the information that's given here, all right? So that's sort of what this is that you take a quarter of a piece of the pie and then you break it up even into further sections, further pieces, and you have a skinnier, taller piece, and that's kind of what this is. On the amplitude side, this is the height of it, okay? And this number here happens to be 67, but look at the end of, you got to remember, the end of the chart here, this is 67 here. It's not only 40 hertz. The 40 hertz goes this way, horizontally. The 67 is here, that peak there, and that's 67 right there. And this is, remember, this is decibels. Negative, it's in the negative range because the pico is 15, 15 decimal places after the zero, I guess before the zero. And so that's 67, this number here for the our peak right there. For mode 2, the yellow, that's 27. And then we have this one here is 14. The peak there is 14. Then the peak here is 15. And so they're really close in strength. Again, this is amplitude, so this is intensity. This is the strength of the signal. This is not bing bing. This is not the harmonics. This is not a horizontal frequency. This is not 67 hertz. Please don't ever call it that. Even though it's rising to a vertical frequency, it's a spike. You see, it's a line. It's not a peak like that. It's a line. It's just a quick hit. It hit it and quit it, right? And these lines are smoothed out. It's not showing you the jagged, ragged edge because this is being scanned. Okay. All right. So when people look at these things, they anthropomorphize in the same sense that, the big Punisher thing, like it was, I'm not going to pull up the post because I thought it was stupid, but it just gave me the idea this is what people do. It's the same exact thing with the cave drawings in Lascaux, in France, and all over there in over caves, so they have caves all over the world. They have drawings, and in other places as well that are considered historical sites, they have these drawings of and carved into the stones as well of odd-looking shapes. They're abstract when you look at it from a narrow perspective, but there are natural principles, there's natural processes of things that are around us that if you had to explain it, it would be in a pattern of a person or a being or something, And so that's where, that's been around for humans since the beginning. This need for pattern recognition, friend or foe, feast or famine. Is it food or do I get a run, right? What are the signs? What am I looking for? And so that process is exactly what humans do. It's exactly what's going on, and that's how people are looking at this. All right. So, in case you didn't know, this is my website here. Schumann resonances. Okay. And I'm going to bring you over here just so you can see what's happening here. There we go. Schumann resonances. All right, there's my website. All right. So this is a post in my blog. Okay, the link should be in the description, I'm hoping. So I'm just going to read these two paragraphs because the overview, I posted this, what follows here, but I posted this before elsewhere. I change it a little bit day to day, but I've already gone through this. So this video is relatively short. That's why I took the introduction out of it. And so what I'm saying here in the blog is it's a common condition in understanding the Schumann that it's easier to make up explanations than it is to become informed on a topic. Okay, so but part of this, I'm being a little, kind of pithy, I don't know, or pissy, I don't know what that is, but when I say people want to see a planet or a sphere or other circular image they recognize. Okay, so this is part of, the need that humans have, a pattern recognition. And I'm trying to respect that, yet at the same time, I'm trying to respect that. But at the same time, the observer, you, on the other side of it, you have to pull back from seeing, inventing a circle or a sphere in there. That, oh, maybe it's a planet, right? Can we both have that kind of compromise here? Where I won't berate you for thinking it's, a lollipop or a tree in there, and you can hold off judgment that, well, maybe it is a planet. Can we have that compromise here? I'm just asking. I don't know. But I'm trying to be better in my approach to the sub-basic stuff of the interpretations of these things from the whack job perspective. I'm really trying to work through the stuff I have for the people throwing stuff into this that is nowhere near close to anything in the technical aspect of it. I'm trying to work through being not rude to people who don't have a clue. at the substantial level. Okay. So one of the things that I'm working on is trying to kind of expand the way I approach this with people to help work through the mental aspect of what may be in people's way of understanding this clearly. Right? You have to, sometimes it takes a matter of unlearning stuff before you can get the good information in. And that's part of what this process has been about, is to give people good information, and in addition to kind of unraveling the mess of the language that was there before I came into the picture. Okay. So as I say here, people want to see a planet or sphere. It's part of pattern recognition. I understand that. Between 17 and 13 right here, the 17 or 7, a UTC 7 to UTC 13, we see an interesting pattern. It's been called a spherical object in the Schumann. All right, so mystically, magically in there, it became a sphere. All right. So is there a spherical object in the Schumann, or is it simply folks can't read the information? All right. So let me show you what I'm talking about. Once again, look at all the complete data. We can see the dependency of frequency has dropped out at 7 when we see the shape appear. And so I made a little diagram that I'm going to show you. We can see frequency. One needs to observe the actual data of the dependencies. This is telling the observer what to see on the spectrogram. This is not new. I keep saying this. You have to look at all of the data, the dependencies. This right here is the dependency of amplitude. All of these, I always give you the dependencies, because otherwise, how do you know what you're looking at? Question mark. You don't, comma, is the answer. That is telling you what to see in the spectrogram, is the dependency. It's difficult for people to see such a perfectly round shape and not think that it's artificial. The problem is that this shape is not as perfect as people want to believe it is. The bottom of it, which you would see as the top of the spectrogram, is flattened. I would imagine that if the shape were as perfect as people think, then perhaps it would be manufactured. All right. So I have gone through, let me find it here. I've been through in this discussion before. Oh, please, system processing, please wait. All right, there we go. All right, so I have been through the discussion before. Our Wages World had a, oh, there we go. All right. So Wages World, in one of his videos talking about the Ezekiel's wheel, okay? All right. This is not a wheel. I'm not saying that. However, we're looking at, boop. When I was talking about the frequency dropping, this is what I'm saying, all right? Dropping, it's dropped out. You see that? That dropped out. The white one was the only one that didn't drop, right? But it's already kind of low as it is. That number's 8, and this red one is at 26, and the green one is at 30. All right, so let's look at this a little bit more. All right. So you see this? We seen it up good enough? All right. So this is a spectrogram. All right. You have this kind of bulge here going on. You have a flat line. See that? A dip coming in there. All right. See all this gray, not gray, a rust color, right? Ding, ding, ding. Our oranges, rust, maroon, you know. It's a rounded shape, but this is what I'm telling you. This side is just where it happens to be an amplitude. You know, like, all right, we've seen rounded kind of shapes, and this is rounded. It's not a lollipop, right? And no, it's not rounded. It's not, you know, it's heart-shaped. Look at that. See the dip there? Bing! It's heart-shaped. And this is our 7.8 hertz harmonic here. Remember that. So it's centered. I'll give you that. It's centered right on that harmonic. That's interesting. This is kind of floating in the air. All right. But when we talk about, I've given, I'll have to dig up the video on the Ezekiel's wheel and kind of reincarnate that, because I've given in there some scientific research and papers where I've talked about the curve, how you could get that the curve in there, because it's a wave. Boop, you got to remember that. Where am I? It's a wave. All right, so you got to remember that it's a wave. There's already a natural rounded shape, and with the resonances, boop, you can get rounded shapes in there. It exists out in nature. You know, like, you gotta see that. It actually the rounded shape of the waves actually exists as a real thing in nature. All right? And water does one of these. It kind of tumbles. Boop. In its natural environment, water is always doing this, right? So when we talk about a current, it's motion. It's always in motion. And you, probably more you than me, we don't look at this from the perspective of it tumbling. Most people don't, but that's tumbling, and it's twisting, it's turning. So you're likely to get, like, whistler signals show up as a, you know, like, boop. I've shown this. I have shown you in the past in other videos that very thing of the signals. Oop, there we go. There we go. All right. So I have shown you in the past these signals that have a whoop and a curve and and a sine wave, a sine curve to them. Right? It is a thing to be expected if for no other reason than mathematically it's programmed into the machine to accept that. It's a wave. It's what waves do. It's waves like that. So the modes are already programmed to accept a wave function in there and sizes and shapes of waves. Okay? And you also got to remember, like, look, around this, around the edges of it is green. It's not just white, too. You have to remember that all the way. Fringed around it is also green. And this is the bigger, heavier part of it as well. So whatever the white is doing, you have to remember that fringed around it are the rust colors, the red, the yellow, and the green. Look at that. All the families represented. There's white, there's red, there's yellow. You can see yellow there. And there's green on the outside. And then there's green, not only green. See this? That's an aqua teal kind of color. You know, these are the different, and are fringed with teal. This is all teal. Look at this, teal, teal. And this right here is rust. And you're getting that from these two. The rust and orange color are the two of these together, red and yellow. And it's the same thing here. You see the red and the yellow acting together. All right. All right, so I wanted to show that. And so I'm going to, again, I've already gone through this. This is old, but, you know, please feel free to read it. So, this here is not a big, this is quality. I'm on the quality dependency right now. So the quality is the magnetics. Okay. So there's synchronous mode. What I call a synchronous mode is it's like nested dolls. So whenever you have these identical looking spikes, you know, close enough to identical, this is coming from high up. This is high voltage. That it's all the same across the shapes are all matching up across the whole spectrum. That's what this is. So it's getting the whole spectrum of the signal. So that's coming in from, you know, what people call incoming. You know, that's what this is. So it's high up in the atmosphere. And this right here is the local time. We got 9, 10, 11, 12, 1, 2, 3. All right. So this is the middle of the day right here. See, this is coming in the middle of the day. This is coming in the middle of the day as well. You see the diurnal variation in the signal. That's this kind of bigger 24-hour pattern right here. And then you have the quality. A lot of times the quality is just kind of all over the place, but not today. This is a very calm in the magnetics. And you got to remember the magnetics travel around the world. Okay, it's been around the world, and the amplitude is quick, it's fast, it's a burst, and doesn't stay as an amplitude for very long before it starts converting, starts degrading into the quality. Amplitude stays upright for a little while, but then it starts degrading as it goes around. You know, it moves quickly, so you know it the speed of light around the Earth is 8 times in a second. You know, so its light has made itself, or the radio waves have gone around the Earth 8 times in a second, right? So by the 8th time, it started to, you know, kind of divulge in 1 second. It's gone around 8 times, and so as it goes around each time, it's kind of splitting down, 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 and as it meets itself, or an earlier part of itself, the part that's in the back, right, which is still getting converted from up there. It's in the back, it's the caboose. So as the engine goes around the world, meets up with the caboose, it starts kind of intersecting it, it starts interacting with it, and splits, it starts splitting up, right? And that's what the harmonics are here. That's what these guys are here, is it's the wave has met the front has met the back a few times, and it's, you know, now we're getting into hours, and it's like these don't last very long, but all of these waves come. You got to remember that the magnetics are lasting longer, generally speaking. The magnetics are lasting longer than the electrics. But this is interesting today. Actually, yesterday. This is yesterday. This is interesting because the magnetics were active during this. So the magnetics were active during that, but stopped soon. Like it didn't keep going for much longer, and then it calmed down. This is interesting. You don't all. This is an interesting pattern today. You don't often see this kind of thing. So the magnetics responded. This is actually before. The magnetics are happening before. See this little spike here? That's not much there. This is big, huge guy here in the yellow, and that number is 17. This is picoteslas. All right, so this is not a big number. This is not strong magnetics. A lot of amplitude going on here. Okay. 8.19. The frequency here, this is kilometers. I gotta remember that. And it's the measurement from wave to wave from peak to peak. Where am I? Boop. From peak to peak. Okay. So that's what these numbers are, is kilometers. 14.6 from peak to peak, 14.6 kilometers. From peak to peak here is 25 kilometers. That's why these numbers are smaller, because the wave is smaller. It's higher in amplitude. It's a smaller magnetic wave, right? That's 14, that's 17, that's 14 and 16. All right, they're not that strong, but usually that number is the lowest and it goes up as it goes down. You know, the same thing here. And you got to remember the quality and the magnetics are intricately linked. I'm sorry, the quality and the frequency. The quality and the magnetics are the same thing. The quality and the frequency is a measure of the frequency is a measure of the quality. All right. So the quality, what you're seeing right there, this is the speed that these waves are going. This is not the harmonics speed. This is not, don't put 7.8 in there. So, you confuse yourself. You don't know what you're doing, you know, and people, I've seen that on Disclosure News, and it does a big disservice to what this is, because people are thinking that this is the harmonic free. It's confusing. If you put a 7.8 in here, you're confused, because this is not the right measurement. This is the harmonic measurement up here, the resonance up here. This is the wave. If you, I've described it this way before. If you took an instrument that would produce sound, this would be a violin. The yellow would be the viola. This would be a cello, and the green would be a string bass. If you can picture the type of instruments that would make those waves, those resonances, there you go. Right? I think that is the best analogy to give people, that you have to look at the modes as the type of instrument that'll produce a certain range of frequency, you know. So the violin, and there's other, like you could have a piccolo or something like that, but you know, piccolo and then a flute and then a bassoon or whatever. It doesn't necessarily matter, but I know stringed instruments well enough to know the four types of, you know, string. Like I said, the violin, the viola, the cello, and the bass. Okay. It's a simple, right? I can't make that any more simple, you know. So all right. So all right. So this is almost at 30 minutes. All right. So I think this is a full video at this point. I'm just addressing the issue here of this, you know, spherical object here, which it's not really an object. It's a, you know, it's an image in there, you know, an artifact. I don't know. It's just a shape. It's just a random shape you recognize as having a, you know, a value, an intellectual value. All right. So that's it for this video. I'm going to close this, and I still got some more stuff to talk about with the solar weather and all of that. There's been a recent CME coming off the sun that's going to hit us soon. It's like on its way here. And so I'm going to end this at like right at 30 minutes and just do the next video soon, I think, like right now, as I have a little energy. So thank you all for being here. I appreciate the love and the support. Thank you for the comments. Thank you all for being here. I appreciate everyone, your love and your support. And thank you all for being here. I'm doing this here with you. The few of you who've actually learned something and benefited from this, I'm here doing this for you. So I think on that cheery note, have a wonderful rest of your day, everyone. Thank you for being here. Namaste.